When we derive the current equation of the MOSFET, we assume that everything was ideal, but it is not so. There are so many non-idealities in a MOSFET, which we'll see in detail in this session. We'll start with the first non-ideality, the mobility degradation. Just recollect that the MOSFET has two electric fields, one vertical and one horizontal. For mobility degradation to occur, the vertical field strength VGS by Tox should be high. When it is high, the carriers start to follow a random motion. As VGS is increased, the speed of the carriers increases, they get scattered, and mobility consequently decreases. So IDS decreases, or in other words, IDS is lower than expected. While we derive the current equation, we assume that the carrier drift velocity increases linearly with the lateral electric field. But in practical situations, the carrier drift velocity rolls off at high field strength and eventually saturates. This non-ideality is called velocity saturation, and under this condition, the carrier velocity can be given as Psat is equal to mu into Esat, which is equation number 22. Including this, the drain current changes into IDS is equal to Cox W into VGS minus VT into Vsat, which is equation 23. Remember, the current equation without considering velocity saturation was beta into VGS minus VT the whole squared divided by 2. Every junction has an associated depletion region. The width of the depletion region increases with reverse bias. When you have a look at the figure, you can find out that the channel length L is reduced due to an increase in the depletion width. This reduced channel length causes IDS to increase. So, IDS, which was supposed to remain constant in the saturation region, is not constant anymore, but it has a slight increase. This non-ideality is called channel length modulation. To incorporate this, we have introduced a factor 1 plus alpha into VDS, which makes IDS to be equal to beta into VGS minus VT the whole squared by 2 into 1 plus alpha into VDS, which is equation number 24. The analysis was done till now by considering only the gate, drain and the source. But there is also a fourth terminal, which is the body or the substrate. VSB, or the voltage between the source and the substrate, should normally be kept equal to 0. This is done in order to keep the source bulk and the drain bulk diodes to be reverse biased, or it is done to stop current from leaking towards the substrate. Let's assume that the voltage between the source and the substrate is not 0 and it is a slightly greater value. This causes the depletion width of the PN junction to increase. Now, if a channel has to be created, VGS should be more, or in other words, the threshold voltage has increased. This fourth non-ideality, the body effect, causes the threshold voltage to increase. The increased threshold voltage is given by equation 25. Here, Vt naught is the threshold voltage which is calculated without considering the body potential. Phi s is the surface potential at threshold, and gamma is the body effect coefficient. Phi s, which is the surface potential at threshold, is a very important equation, and it is given by equation number 26. Phi s is equal to 2Vt ln of Na by Ni. Na is the acceptor concentration. Vt is the thermal voltage, which is equal to Kt by Q. The ideal transistor assumes current between the source and the drain only when VGS is greater than the threshold voltage. Practically, IDS does not drop to zero when VGS is less than VT, rather, it drops off exponentially. This current, which occurs below the threshold voltage, is called a subthreshold conduction, and it is it's something which is not desirable, and it is called a leakage current. So this brings about the fifth non-ideality, the subthreshold conduction. The next non-ideality is DIBL, which is drain-induced barrier lowering. The barrier gets lowered by a large positive VDS. This enables the electrons to easily cross to the source. This causes VT to decrease. This reduced Vt is modeled by equation number 28, which says Vt dash is equal to Vt minus eta Vds, where eta is the DIBL coefficient. Ion junctions between the diffusion and the substrate or the well and the substrate form diodes as shown in the figure. The well to substrate junction is also a diode. The substrate and the well are tied to ground or VDD to ensure these diodes remain reverse biased. Even though they are reverse biased, they still conduct a small amount of current, which is ID. ID is given by equation 29, where IS depends on the doping levels, area, and perimeter of the diffusion region, and VD is the voltage across the diode. There is a finite probability that carriers will tunnel through the gate oxide. This is according to quantum mechanics. This results in the gate leakage current flowing into the gate. This occurs when the thickness of the gate oxide is less. The probability of tunneling drops off exponentially with oxide thickness. An alternative to silicon dioxide can be silicon nitride, but still research is going on in this. Tunneling can be used to create electrically erasable memory devices, which is not in our scope. The next non-ideality is something which cannot be avoided, the temperature. PT decreases linearly with temperature. Junction leakage increases with temperature. On current decreases with temperature. This is called negative temperature coefficient, and the off current increases with temperature. Avoid this, can we say that the circuit performance can be improved by cooling? There are many advantages of operating at low temperature. Subthreshold leakage is exponentially dependent on temperature, so lower VT can be obtained. Hello. The last non-ideality is geometry dependence. The mask which is used may be of wrong dimension. For your reference, a mask has been shown in this slide. The next geometry factor which causes non-ideality is lateral diffusion of source and drain. Have a look at the figure. The source and the drain are diffused and they should stop at the arrow mark. But they don't stop there. They go beyond and get diffused even below the gate. This is called lateral diffusion of source and drain. So these are the non-idealities in a MOSFET which cause it to deviate from the ideal characteristics. Thank you.